All right, my good friends, I do want to welcome you back. This is Unit 3, the quantum model of the atom. Hope everything went okay for you on that first examination and there were no problems there. But if you didn't quite score as well as you would have liked to, make sure you take some type of corrective action. Come in for tutoring once or twice a week, or maybe do some more homework problems, or whatever the case may be, whatever you need to do to improve. So here we go. I also want to tell you that these notes for Unit 3 are fairly complete, so I'm pretty much going to narrate. If you have questions, feel free to either pause the video or ask me to pause the video in class if we're watching this in class, and ask me to explain anything that's not clear to you. So here we go. In the early part of the last century, scientists thought they'd figured out the atom, but one interesting observation intrigued them. When hydrogen gas was exposed to heat, the hydrogen gas emitted visible light. Visible light. These scientists knew that to truly understand the atom, they would have to understand the light that was being emitted. This unit is about what these studies revealed about the true nature of the atom. So we're going to temporarily move to a study of the physics of light. Then we'll take our knowledge of light and apply it to better understand the atom. So here goes. The wave theory of light. Our current understanding of light is that it travels as waves. These waves are similar to the waves that would be generated if a pebble is tossed into a pond. Light waves, however, are made of energy. Let's examine a wave and define some of its parts. So this is a wave, right? It's not unlike a wave that you might see at the beach, or you might see with young girls, or maybe even young girls and boys, jumping rope on an elementary school campus, right? Now, we're going to define some of these parts of the wave. The first one we want to look at is called the wavelength. And the wavelength is the distance from, we can say, the crest of one wave to the crest of another wave, or we can say the trough of one wave to the trough of another wave. Or we can just generalize and say from any point on a wave to the successive point on the next wave, just like that. All of those have the symbol lambda, and lambda is drawn or written like this. It's kind of like an upside down Y, right? So wavelength is the distance, usually in meters, from any point on the wave to a corresponding point on the next wave. Now amplitude. Amplitude is the distance from the middle of the wave to either the crest or the trough. They're the same length, okay? So the amplitude is from the center to the crest or the center to the trough. All right? The wavelength, again, is the distance from the peak or the highest point of one wave to the peak of the next, or the trough, the lowest point of one wave to the trough of the next. Wavelength is often represented by the lambda symbol. Let me write that for you one more time. It takes a little practice to be able to write it. It's kind of like an upside down Y. It's just like that. The amplitude of a wave is distance from the middle of the crest, middle to the crest, or the middle to the trough. So we've already mentioned that. So we've got under our belts now a couple of different definitions. We know what wavelength is, and we know what amplitude is. All right, good. Let's move on. A period is the time between the passing of successive crests and is measured in seconds. All right, that's a period. Frequency is the number of crests passage per second and is measured in waves per second, or hertz. This unit will be very important for us. Okay, and we write frequency sometimes with a kind of a cursive F, but most of the time we write it with kind of a cursive V. In fact, it is a cursive V, right? So, period, the time between the passing of successive crests, measured in seconds, and frequency, the number of crests passing per second, and measured in waves per second, or hertz. And finally, we need to know the speed of light. In a vacuum, it's 3.0 times 10 to the 8th meters per second. The lowercase c is used to denote the speed of light. So that's the speed of light, right? That's the speed with which light travels in a vacuum, 3.0 times 10 to the 8th meters per second, all right? And it's, again, often denoted with the letter C. There's a very important mathematical relationship between the speed of a wave and its frequency and its wavelength, right? The velocity of a wave is equal to the wavelength times the frequency. That's this relationship we're talking about. The velocity of a wave is equal to the wavelength times the frequency. So if light is the wave that we're talking about, then we can say that c, the c is the symbol for the speed of light, is equal to wavelength times frequency. So this relationship implies that since the speed of light is a constant, that wavelength and frequency are inversely proportional to each other. If one is high, the other one has to be low. So let me make that point again. C is a constant. That's the speed of light. So if the speed of light is a constant, then these two numbers have to be inversely related. If one of them goes up, the other one has to go down. If the wavelength goes up, the frequency must come down, and vice versa, because C cannot change. Albert Einstein demonstrated that the speed of light is constant in a vacuum. In 1928, Max Planck came along and said, I'll go one step further. The amount of light and the amount of energy which a wave possesses is equal to a constant times the frequency. Of course, he called the constant Planck's constant, and it is symbolized by the lowercase letter h. So here it is. This is the formula. It says that energy is equal to Planck's constant times the frequency. Energy is equal to Planck's constant times the frequency. So the energy in joules of a wave is directly proportional to the frequency in hertz. The greater the frequency, the greater the energy. All right, now note, Planck's constant is this number. It's 6.626 times 10 to the minus 34. And that unit is strange, but it's absolutely correct. That's not a typo. It's joule seconds. You've never seen that kind of a unit before, so this is the first time. It's 6.626 times 10 to the minus 34 joule seconds. So again, this relationship, very important. The energy of a wave is equal to a constant called Planck's constant, which is 6.626 times 10 to the minus 34 joule seconds times the frequency. So the greater the frequency, the greater the energy. That's what Planck contributed. Now what we want to talk about is the electromagnetic spectrum. Visible light represents just a small part of the electromagnetic spectrum. There's all kinds of energy traveling through our universe. There's visible light, ultraviolet light, infrared light, radio waves, microwaves, X-rays, gamma rays, and even more. And all of these types of radiation fall on a spectrum called the electromagnetic spectrum, right? So here it is. Here's the electromagnetic spectrum in wavelength from high to low. So radio waves have a very high or great wavelength, right? About 10 to the third meters. But gamma rays are very small. They have a very small wavelength, only 10 to the minus 12 meters, right? So as we go from radio waves to microwaves to infrared, visible, ultraviolet, X-ray, gamma rays, we're decreasing the wavelength. So what are we doing to frequency? We're increasing the frequency. So what did Planck say about what happens when we increase the frequency? Well, energy was equal to Planck's constant times frequency. So if the frequency increases, the energy increases, which means gamma rays are high energy. Radio waves, on the other hand, are low energy waves. So we mentioned visible light. Visible light is on the electromagnetic spectrum. What does that mean? Well, it means that a small part of the electromagnetic spectrum in the universe, a small part of all the waves that are in the universe, are visible to the human eye. And these are the frequencies from 10 to the 4th to 10 to the 20th, right? So we can see a small part of this spectrum. We can't see radio waves, although we know they're there. We know that there are radio waves in the room right now, because if I were to turn on radio on, it would play, right? There are all kinds of waves around us, but only visible light is the one type of electromagnetic radiation that we can see. So gamma rays on the far right have the greatest frequency, so they have the greatest energy. Radio waves have the lowest frequency, they have the lowest energy. To remember the order of visible light, use this. Roy G. Biv. You probably learned that in elementary school. Red, orange, yellow, green, blue, indigo, and violet. Now, red is a visible color and lower in energy compared to violet, which is higher in energy. So we're going from low energy to high energy when we say Roy G. Biv. But that's the order of the colors of visible light in the electromagnetic spectrum. Roy G. Biv. All right. In about 1924, scientists discovered that when energy was applied to hydrogen gas, the gas emitted light. But interestingly, not a spectrum or a smear of light, but only light at 4 distinct energy levels, right? So when energy was applied to hydrogen, only 4 bands, one here, one here, one here, and one here, could be seen. It wasn't a spectrum, but only 4 bands of light. Well, what did that mean? Niels Bohr was carefully watching these studies and formulated a hypothesis about the atom. Perhaps he thought the energy being generated in causing these distinct light bands were electrons of hydrogen atoms being energized, but then falling closer to the nucleus and releasing photons of light at specific wavelengths. In other words, as the electrons were heated, they absorbed energy from the flame, but eventually that energy would be emitted in the form of light, and that light was visible. Okay? It was an astounding hypothesis that implied that since only specific frequencies of light were emitted, the electrons were falling down from specific energy levels. Bohr's hypothesis was elevated to theory status when he proved mathematically that this indeed was occurring. So the Bohr model of the atom was born. No longer was it thought that electrons were scattered throughout the atom like plums in a plum pudding, but now, because of this new mathematical evidence, it was believed that the electrons existed in specific orbitals around the nucleus, like planets around the sun. Okay? So when electrons were heated and they fell into lower energy levels and eventually they fell to specific energy levels, and that was the explanation why when hydrogen gas was heated, those electrons were emitting only specific frequencies of light. This helped to shape the Bohr model. As electrons were energized, they absorbed energy and moved further away from the nucleus. Eventually, they lost the energy and moved closer to the nucleus, emitting energy packets called photons. All right? Photons. Folks, I think that's going to do it for this one. The important thing is that we have now some basis for the atom. Not just a hypothesis, but a theory that explains why we see only specific bands of light. It's likely because the atoms are falling from specific regions surrounding the nucleus called orbits. I'll see you in the next one. Thanks. Bye-bye.